So welcome to this session dedicated to cryosphere change innovation in observation and modeling. This session has been jointly organized by Eurac Research and CNR Institute of Polar Science. So I'm Claudia Notarnicola, and I'm the director of the Institute for Earth Observation of Eurac Research, and I will be the moderator today. So first, of course, I would like to thank all the speakers who have accepted to be part of these sessions, and also that we a bit organized together the idea of these different talks. So what is the rationale? So Arctic and Alpine, as well as high mountain research communities, are facing interconnected challenges regarding climate change. And we know that this region are also, as we saw in the other session, are also facing an amplification of the different effects related to climate warming. So in this way, by sharing the different methodologies, the insight, the aim is to strengthen a bit the global strategy for this cold environment. So before to start, I want just to remind that more or less for each presentation we have roughly 12 minutes, so I will give then some signs before the end, and just to give a bit time at the end to have some questions and comments. So then I will give the floor to Thomas Nagler, that he is the director of ENVEO in Austria, and the talk is dedicated to monitoring Greenland ice sheet dynamics and surface condition in a changing climate, current status and emerging opportunities.
Okay, thanks Claudia for this introduction. In this talk actually I am focusing on the status of monitoring Greenland, but I want to point out that we are not only doing this for Greenland alone. Actually we are using the complete Sentinel family of satellites available through Copernicus, but also third-party missions, in order to get a view of all the polar regions on the southern and also on the northern hemisphere. So including Antarctica, but also we are looking to smaller ice caps in the south and as well as in the north. As this workshop is more or less on the Arctic, I want to point out that of course Greenland as an ice sheet is dominating the land ice in the Arctic, but nevertheless Svalbard and the Canadian and Russian Arctic ice caps are also of importance, and we are observing there big changes. But in this presentation actually I will focus primarily on Greenland, and this work is actually carried out in a couple of projects by ISTA, where R&D is carried out towards the services, and currently operational production is carried out in the Copernicus Climate Change Service on the Cryosphere domain, which started 1 year ago and is continuing hopefully in the next years. Now, what are we doing actually for Greenland? We are using Sentinel-1 in order to look for the ice dynamics. So this is an example from 2014 onwards. We are producing annual maps of the ice velocity in order to look for the dynamic changes which are caused by climate change in this region. The products actually are available with 250 meters. They are gridded, averaged over 1 year. And they are primarily based on Sentinel-1 data. The method what we are applying is primarily offset tracking, but in the later time we are also including ISAR interferometry for this. And this started already more than 10 years ago in order to provide these products. And they are available also through various data portals from Copernicus, but also through the ESA Climate Data Dashboard. And I also want to say that there is a lot of data involved, so it's a big processing task. And there's a full validation carried out for the scenes. They are providing X and Y components of the velocity, but also for every pixel we are providing an uncertainty measurement, which is not shown here. Annual velocities are quite interesting, but more interesting is seasonal changes of this. And therefore we are looking also for generating monthly products of the ice velocity. So they are starting in October 2014, and this is a continuous processing. And you see that there are still a couple of white gaps in the center of Greenland. This is because there is no continuous acquisition all over the year. We have a winter campaign during December until end of February, which is covering complete Greenland. And during the summer months, we are primarily focusing on the margins, which are continuously observed. And this is, of course, important because then we can calculate also the mass fluxes towards the ocean. And this is, I will show a little bit later on. So we are using here, in principle, Sentinel-1A and B satellites from 2014-15 onwards with 6 days repeat. With 2021, there was a failure of Sentinel-1B, and we only had 12 days. And now, since a year, we have again with 2 satellites in space, C, and now since a few months, also Sentinel-1D, which will guarantee us in the next couple of years a very good coverage. And we also know now that we are revisiting the acquisition planning together with ESA in order to get a continuous overall coverage of the ice sheet all over the year. Now, what can we see from this? And I select now an outlet glacier, Jakobshavn, which is a dominating, or the fastest glacier in the world. It's very famous. It is producing a lot of icebergs draining into the ocean. And we see a high seasonal variability. This was not known before the Sentinel-1 area because we had only ENVESAT and the snapshots every couple of months or half a year. And now we can really follow on a monthly basis or even with high resolution the dynamics of this glacier. And what we see is that there is a big seasonal change in the velocity. It ranges from about 20 meters per day with an ice front of 5, 6, 7 kilometers width and a depth of about 1 kilometer. And the maximum we reach in the summer up to about 40 meters per day. So it's almost a doubling between the winter and the summer season. And of course, we see that there is also an annual change. So it's not every year the same. Just as an example, how another glacier in a different regime is. Now we're looking to Biedermann Glacier in the north of Greenland. We see it's draining towards the Arctic Ocean. And we see that there is a peak during the summer months. And the points actually are located along this central flow line. The color code exists here. And we see that at the, close to the margins of the glacier, we are going here only to about 4 meters per day during the summer period, and a little bit lower, let's say 3.2 meters per day during the winter period. But it's kind of systematic seasonal variability. And then, of course, this is very important in order to calculate the mass fluxes. Now, in order to calculate the mass fluxes, we use on one hand these products what we have shown before, but we need also additional information, and this is coming from airborne campaigns or other observations. And what we are calculating is actually the flux of the ice through a defined gate. The gate is on the best case located at the grounding line where the water starts swimming in the ocean before it is on the ground landed, and where it starts swimming, it belongs not to the ice sheet anymore, it's an ice shelf or belonging more to the ocean. And then, of course, we can calculate with the ice velocity and the thickness along the gate the drainage of the ice into the ocean. And this is calculated now for another glacier in the north of Greenland, the Academy Glacier. And what we see is that there is, of course, a seasonal cycle, which is caused by the velocity. But we also see that there is an annual variability from increase up to about 2019. Then there was a break-off of a big iceberg, and then it slowed down again. The iceberg drifted away in the ocean, and then we are actually coming up again slowly, I have to say, to the previous amount. And not every glacier is behaving the same. So we are looking to more than 250 glaciers in Greenland, and this shows you a map where we are looking for the change of the ice discharge for these more than 200 glaciers across Greenland. And the increase of the ice is shown in red compared to the previous year. A decrease is shown in blue. And the size of the blob here shows you the percentage of increase there. And we see that there are some systematics according to the regime. This is caused by the ocean, but also by the weather on one hand, and the accumulation on the glacier. On the other hand, also glaciers which are next to each other, they have a different behavior. So it's important not only to look to one glacier and say this is the message for complete Greenland. We have to look to all the different or major glaciers in the different sub-basins in order to get a good idea what is going on and what is the response of the ice sheet in response to climate change. Now just some numbers. We are interested in how Greenland ice sheet is performing, and this is from 2014 onwards for the 8 sub-basins. You see those here. They are draining towards the different parts of the ocean. They are derived from the ice velocity field and collecting different glaciers which are draining to a certain part of the ocean. They are, of course, different in size, but I want to highlight here the black line, which is the zoom of complete Greenland. We see a kind of increase from 14 onward. The seasonal cycle is also shown, but the trend is shown on this line. And in the last few years, we see that there is no significant increase anymore. It's more or less keeping at the same levels. And we are providing these numbers on the annual mass discharge shown here. And there are, of course, always these, this is in gigatons per year drainage. So the average is about 480 gigatons per year with the uncertainty of about 60 gigatons per year. Now, another point is we not only want to look to the change of the ice dynamics. Another important factor for looking to the response of the ice sheet is the surface melt. So how far is the surface melt going to the inwards of the glacier? Stays it just outside at the margins, or how far is it reaching inland to the ice? And for this, we are looking to daily time series of backscatter. So again, C-band radar data. And this is, I will not go into the method in detail, but we are discriminating 3 or 4 different phases of the snow conditions. So there is this winter phase where there is no melt. Then there is a phase where we identify an active layer of melt on the surface. So the surface is wet and we see that it's melting. Then we have an intermediate layer where the SAR signal or the C-band signal is saturating. This is shown here in black snow. So we know that it's wet snow, but the signal saturates because of the sensitivity of the instruments. And then in autumn, actually, you see here this in yellow, when there is a refreezing, backscatter goes up again. And this is that on top of the wet snow, which is shown in this sketch here, we have a refrozen snow layer, and due to the atmospheric forcing, it's getting colder temperatures, the thickness of the refrozen snow is increasing in time, and we have still a little bit of wet snow below, and therefore we see the increase of the backscatter. Now we can actually look this, how Greenland is behaving, and we are calculating this for on a daily basis from ASCAD data with about 4 kilometer pixel spacing. And you see the breathing in principle. So it's a very dynamic process which is responding to atmospheric forces, but of course also on the climate itself. So these light bluish colors show you where the snow is actually starting to melt on the surface. The black, the darker bluish colors is where we have the saturated signal, but still melted snow. And then we have the increase of the refrozen snow. This is with 4 kilometers, and it's a very nice product for looking for the complete ice shelf. But when we look to the mountain regions, then we need a higher resolution, and therefore we are using Sentinel-1. Currently, Sentinel-1 gives us not that high spatial, a higher spatial resolution with about 100 meters, but the temporal resolution is only 6 days. So this is a kind of trade-off. The aim is, of course, to combine both products in order to get in complex terrain where we have the fjord glaciers, making use of the higher resolution of Sentinel-1. In the interior, we can still go with the ASCAD data. This data set can give us also some climate information. We can look for, and this is now done for 2012, so the mean melt days from 2007 to 2020, so the bluish colors, so white is 0, it goes up to half a year, in days 180. Then we can look for the melt days in 2012. Why did I select 2012? This was a record year for surface melt where we reached already very close to the summit. And then we can look for the anomaly for this 15 years period for 2012. and the melt occurrence for the complete. So to look which regions are melting in this 15-year period. And we see, of course, the margins are melting in principle every year, but when we are going towards the summit, the melt occurrence is quite less. So very quick, the summary. So we have with the Copernicus satellites, we have excellent tools in space in order to look for short-term and long-term variations of ice speed. And this gives us really a new insight into the processes and also the discharge of the outlet glaciers. They are different for every glacier, and we do this not only for Greenland, but also for Antarctica. There are many more glaciers, and the mass flux is more. But it shows us that also in Antarctica, there is a change in this ice discharge. The major uncertainty in this is actually ice thickness data, but there are new data coming up from airborne campaigns. For example, the RINGS campaign was just completed, and the data are in processing. RINGS campaign was a campaign where a consortium flew around Antarctica in order to measure with airborne systems very accurately the ice thickness. With ACECAD, in combination with Sentinel-1, we have excellent tools for looking for the ice surface melt and its dynamics. And what we actually need is a year-round ice sheet-wide Sentinel-1 coverage. So this is now in planning, so that we can also go with Sentinel-1 to the interior during the summer periods in order to detect early changes in the ice speed and look them in detail there. And with the upcoming expansion missions, especially ROSE-L, but also now with NISAR, we expect further improvements, and we are working on the integration of this satellite data into the processing lines. Okay, thank you.
Thank you, Thomas, for this nice talk. Then we move to the second one, which will be given by Francesca Pellicciotti. She is a professor at the Institute of Science and Technology in Austria, and she will talk about the use of surface model to understanding the changes in the cryosphere, Megadroughts, and the Pamir Karakoram anomaly. Thank you.
Yes. Good morning to everybody, and thank you very much, Claudia, for inviting me here. This is the short version of my talk. The long title of my talk today is How Land Surface Models Can Advance Modeling of the Cryosphere in a Changing Climate. And I'll be talking about two case studies, Megadroughts and the Pamir Karakoram anomaly. But I would like to start from recalling how we can model mountain systems and what we mean by land surface models. This is a schematic representation of a mountain system. There are glaciers, there is snow. And traditionally, we've been looking at those systems, including permafrost, for instance, in a very silos approach. I mean, glaciologists look at glaciers, snow scientists at snow, etc., etc. And I'm claiming today, and I would like to convince you, that I think we can use now, because of a number of new opportunities, a new generation of models, so-called land surface models, that can solve the energy, mass, and carbon fluxes for every grid cell of those systems. So they use a fully distributed representation of the system. They solve, as I said, energy, mass, and carbon fluxes with fully physically based equations. The main disadvantages of these models, of course, is that they have very high computational cost, and I'll come back to this later. But the main advantage is that they really are a holistic representation of all the system. We can understand the whole system functioning, and especially we can integrate a large variety of very different type of data, both satellite data and ground observations. I'm going to discuss today two cases where we were using that land surface model that in my group we have been developing over the past, I would say, 6 to 8 years, to ask two key questions. And the first is the so-called Pamir Karakoram anomaly. So this figure here shows, this was published some years ago now, for every glacier in high mountain Asia, every glacier is a dot, the mass balance. I mean, Thomas was talking about mass balance, so it's the mass losses or mass gain of every single glacier in high mountain Asia. If it's red, it's mass losses. If it's blue, it's mass gain. So in this case, for instance, -1 means that on average over 1 year, the glacier, on average of its entire surface, loses 1 meter of ice. And you can see that high mountain Asia, Himalaya, Hindu Kush, and then Tien Shan, this is the southeastern Tibetan plateau with very high mass losses. On average, is everything red except for this region. And this has been called the Pamir Karakoram anomaly. And those, in fact, let me go back. Those results, they come, it was great that Thomas had his presentation before, because we used satellite images. This was the work of Etienne Berthier group. And then we use ice velocities, which is a great from satellite, which is a great product, to calculate the surface mass balance using the continuity equation. Now, so this started from satellite images that I think are a great way to get the picture of what is going on at the moment in the present. Then another paper from the same group came out. This is Romain Hugonet and co-authors' work. In 2021 in Nature, they published the global estimate of mass losses, well, of mass balance for every glacier on Earth, with very high uncertainty in our region. But if you zoom, this is the Pamir and Karakoram, and you see they also produced 5 years intervals. And you can see that from 2000 to 2020, what was yellow and blue is getting reddish. So glaciers also in the region are starting losing mass. Now, there are very high uncertainty on that global product. And the question that we as modelers were asking is, okay, is there really this evidence with high uncertainty of an end of that anomalous pattern? Can we prove that evidence with our models? And can we explain the causes of that? So this is what we did. We used the land surface model that I very shortly described at the beginning of this presentation. We applied to a region in the Pamir, in Tajikistan. And this shows, these are the simulations, aggregated simulations for that region in the Pamir. This is mass balance from 2000 to present almost. And you can see indeed that for the first 10 years, I mean, this is the Hugonet data set arrived more or less was 2018 or 19. But you can see, in fact, that there is a stable or positive mass balance regime, and then starting 2012, and very clearly from 2018, there is an inflection. Those glaciers, for which we have evidence by now that from a number of variety of satellite data that were gaining mass or being stable, started losing mass. Then the second, this is a paper we just published last year too. And then the second question, well, the key advantage of using a model is that it can tell you the causes, what remote sensing cannot do. I mean, the causes of that regime shift. And the causes in that case, that decline in mass balance was a decline in snowfall. And that snowfalls, and this is even more interesting, was due to less precipitation falling in the region and not a precipitation phase change, which is absolutely not a change of phase from snow to rain, which is what is happening in many mountain regions, including the southeastern Tibetan plateau, and explaining those very high mass losses. So then the next question we were asking is, okay, I mean, we were able to identify the causes. Is this just a fluctuation, or is this a permanent inflection of that positive mass balance regime? So we were asking the question, is this going to continue? And the answer is yes, it is. These are simulations without uncertainty bars because they would be very, very high. These are the simulations then with the same land surface model for that same region up to the end of the century. These are the 3 different scenarios. We run 12 GCMs downscale for the region, and you can see that that inflection continues. Now, I just would like to and we were able to calculate all the components of both the runoff changes and the glacier mass balance changes, from sublimation to accumulation and internal refreezing. I just would like to make a comment here that those simulations are as good as the climate models that force them, and those are very uncertain, I would say. And now I would like to move to the second topic for which we use that land surface model. It's quite different. Well, this is where we are now, sorry. That was to say, I don't know if we can trust I can trust the model, but there is a very large uncertainty on the climate models we are using to trust that model. The second topic for which we use a land surface model, and very different, droughts. Droughts are increasing in intensity, frequency, and duration. This is a paper we also published last year in which we were focusing, looking at global droughts, multi-year droughts, and we were focusing on the duration of the drought. And indeed, there are more and more droughts that last more than 1 year. And the question that we were asking is, what is the role of the cryosphere in buffering water deficits during a drought? So this is just a schematic representation. present to the end of the century. Glacier volumes are going down everywhere, probably also in the Pamir Karakoram by now. This is this idea of peak water that contributes water and then they start declining once they reached a critical mass, they shrunk enough. We don't know what vegetation is doing in the climate, in the water cycle of the mountains, but a drought, the point I want to make here is that a drought will have a different impact if it hits a region, a mountain region here, where there is enough mass, glacier mass, or towards the end of the century, where glaciers will have shrunk and lost the capacity to buffer the drought. So the question we were asking is what happens during multi-year droughts? And we were asking that question because we were in Chile when the so-called Chile megadrought hit the country in 2010. We were there in 2011 for fieldwork on glaciers. That led to dramatic water shortages. They had to declare the state of emergency. This was a lagoon. This is a lake. It's no longer a lake. And we were asking the question, where did that precipitation deficit go? The Chile megadrought is still ongoing. 16 years of a megadrought is unprecedented. So where did the precipitation deficit go? So we run for the whole Maipo catchment that feeds the capital city of Santiago, about 30,000 square kilometers, the same land surface model that I was discussing earlier. And now, I don't know if there are hydrologists in this room. I'm an hydrologist by background. So stream flow and evapotranspiration, I hope everybody will agree, are the two ways that water leaves mountain system and hydrological system, the two fates of water. And what happens, so this is before the megadrought, this is 2010 when the megadrought hits the country, and during the megadrought, evapotranspiration overtook stream flow as the dominant outflow. There was a dramatic change in the way the system was functioning. In fact, it went from an energy limited to being a water limited system. And now this is the Maipo. So these are the Andes. There is a border with Argentina and Santiago is here. And this map shows about 30,000 square kilometers, as I said, shows runoff. This is the annual production for every grid cell. These were simulations at a grid cell of 500 meters by 500 meters. So you see this is the average runoff during the 10 years before the megadrought. And this is the change. This is the change during the 10 years of the megadrought. And you can see that there is a dramatic reduction of runoff everywhere in the catchment. This is the brown. Dramatic is more than half. Everywhere except where there are glaciers. You see these are the green areas, and this corresponds one-to-one to the map of glaciers in the region. In fact, glaciers were providing excess water to the system. They were providing more water than during conditions of non-megadrought. These are all simulations with that land surface model. It has it can have an amazing spatial and temporal resolution. These are simulations we run at 1 hour temporal resolution. But the most interesting, another very interesting thing, is that evapotranspiration decrease in the valleys and increase in the mountains. In fact, this is NPP, this is GPP, in fact. This is an index of how the vegetation is doing. This has been called the so-called drought paradox. There was a paper in Nature, quite a famous one, that shows that vegetation high up, if there is the cryosphere, snow and glaciers to support it, will do better. And so we'll evapotranspirate more and enhance the runoff deficits downstream. So you see very clearly there is browning in the valleys and greening in the mountains. Now, the next question that we were asking is if that megadrought had hit the country, well, the central part of the country, towards the end of the century, what would have happened? And I'm going to be brief here. Claudia, do I have a few minutes? Yeah, right. Okay, then I'm not going to be brief. Okay, so these were our simulations for the present. We are here somehow. Sorry, how many? 1 minute. Okay, no, then I'm going to be brief. This is also a paper we just published last year. So towards the end of the century, air temperature is going to increase, total ice volumes are going to decrease. The glaciers will have lost their capacity to buffer, to provide water when there is a precipitation deficit. And to be very short then, the results of those simulations were that in summer, if a megadrought had hit the country towards the end of the century when glaciers have shrunk, we would have lost, there would be a reduction of up to 50% in summer runoff. So, next question, I'm super brief here. What if Megadroughts it's Europe? We have a large project funded by the European community to look at it. There have been no megadroughts in Europe, so no multi-year droughts in the past century, but there have been in the past for paleo record, we know that. This is just an example. We run the same land surface model for the entire Switzerland. And I just want to point you here at 2018 and 2022. They were extreme seasons. This is run of production. And you can see that in 2018, summer and autumn, and in 2022, spring and summer, these are simulations at 250 by 250 meters, a large part of Switzerland was not producing runoff. A very large part of the country was not producing runoff, and the only areas were the mountains. And with this, I conclude, we are now doing the same simulations for a number of major mountain regions in Europe, including the Apennines, in fact, that have very little, no glaciers, I would say. Now, looking ahead, I don't know if I convince you, it was a short talk, but land surface models can minimize equifinality. We can ingest compared to empirical approaches that have been traditionally used in hydrology, for instance. They can integrate a large amount of very diverse ground and remote sensing data, which is what we did to obtain all the simulations I was showing you. They represent the physics of processes. Of course, they are heavy computationally, but we understand how those systems work. We understand the shift in regimes or transition into another regime. And finally, to overcome the heavy computational cost, since they are physically based models, we can build AI emulators for large-scale global simulations. And this is also what we are doing now. And with this, I thank you very much for your attention.
Thank you. Thank you very much, Francesca, for the talk. Now we move to the third talk that will be given by Biagio Di Mauro. He is a senior researcher at the Institute of Polar Science, the CNR, and he will speak about optical remote sensing of alpine and polar cryosphere.
Okay. Thanks, Claudia. Hello, everyone. My talk today is about optical remote sensing of alpine and polar cryosphere, and again I will try to show up some examples of application of those kind of data in alpine and polar region. I will start up directly explaining the motivation of our research. I will say with optical data we can monitor what happens when a glacier or a snow is melting, and often different kind of processes can happen here over a general ablation zone. So you see that there are some albedo feedback. So an albedo feedback means that if you have an accumulation of impurities over a surface, you will absorb more radiation and more melt, and this melt will accumulate further impurities at the surface and melt water. And this further enhance the albedo feedback with producing more melting. So the key question of my research here is what darkens snow and ice and how we can monitor those kind of processes using both satellite data and in situ measurement. You see here that we can have like different type of impurities such as dust or algae that can grow over the surface of snow or glacier ice, and formation also of cryoconite holes, which are a small depression with very dark material that accumulate on the surface of a glacier, absorbing more radiation and create this little hotspot of life, actually, because there is a lot of living organism that stays in this small ponds here. Using satellite data, we can have like for example, for Greenland, an estimation of the snow grain diameter using analytical model or inverting radiative transfer model, and broadband albedo, as you can see in this. Oh, sorry. In this plot here. It was a video, but it's not working because it's PDF. I forgot. So, for example, for broadband albedo, you see there is quite variability over the Greenland ice sheet, where some areas show very low albedo values, and you can imagine that having like 0.2 or 0.3 of albedo for a glacier it's dramatic, because it's absorbing 70–80% of the incoming solar radiation during the summer, and this further sustain the albedo feedback that I mentioned before. Using satellite data, we can also monitor trends of albedo. This is quite an old paper, but I like it because it decouples the effect over the visible and near infrared. we can have an image of a clean snow and ice in mind, but actually if you go in the field during summer, you can have this kind of type of glacier. We learned about this in the Arctic session this morning about snow, but this is focusing on ice. So the question here, is these things accumulating at the surface and creating more melt, or is something related to the melting itself that produce more melt water and accumulate further impurities and so on and so forth. So in this study here, the colleagues tried to decouple the effect over the visible near-infrared and shortwave infrared, where impurities have larger effect over the visible part of the spectrum, and the melting itself, so grain coarsening, it has more effect over the structure of grains, so in the near-infrared and the shortwave infrared. If we calculate, for example, anomalies of albedo, some areas pop up. For example, this part here of the Greenland ice sheet, it often get very low albedo value during the summer. In fact, if you zoom in with a Landsat image, we can see there is this band. It is called the dark zone, because seasonally it gets darker and darker, and you see the formation of melt pond here that also has an albedo feedback if you zoom out and you use like a cursor kind of data. Recently, we've been using new generation of satellite data, for example, Prisma, which is a satellite mission from the for the Italian Space Agency, is an hyperspectral mission, so it collects radiation reflected from the 400 nanometer until 2,500 nanometers, so covering all visible and near infrared and shortwave infrared. And we tested Prisma data over the Greenland ice sheet and over the dark zone to try to decouple and estimate the properties of this kind of surface here that you can see. It's very dark in color, so we were wondering what's causing this darkness. It's something related to living organism or just dust and so on. So first results here, we inverted the radiative transfer model to get this plots here. So we get properties of the surface by exploiting models. In this case, we have ice grain dimension, snow grain dimension, liquid water in ice, liquid water in snow, and glacier algae and snow algae. In particular, if we focus on glacier algae, they are like living organisms that they find the right place to be over melting ice, and they accumulate and create this blooming that looks like this, but actually it's a lot of living stuff there. And we compare with previous observation from another group where they sample on the ground. So sampling on the ground is fundamental for validation of this kind of products, because otherwise we can produce like maps, but we don't know if they are good or not, or reliable in terms of if we want to assimilate, for example, in some models, those kind of data. Zooming in northwest Greenland, we did the campaign over this Kanak ice cap to try to focus and go in the field and try to sample and develop new methods in order to exploit Sentinel-2 data. Sentinel-2 data have been mentioned yesterday on the session, but the interesting point here that I want to stress out that Sentinel-2 has a roughly daily temporal resolution in high Arctic, like in this case. So we have one image per day or each 2 days, some days, so we can really can follow the albedo decrease at 10-meter spatial resolution over this ice cap, and by applying some empirical model that we developed, we can track the growth of glacier algae and describe their phenology. So when they start to grow on the ice, it's exactly when the albedo starts to go down and reach its minimum after that. So using this kind of concept of looking at with a phenological eyes, we started to calculate the glacier algae concentration in terms of mean for each years, and calculating also the minimum albedo reached by each year. So some patterns started to pop up. For example, 2023, you see that all ice cap was reached bare ice condition with very low values, and accordingly glacier algae started to bloom all over the ice cap. Some other years the snow remained at the surface and prevented the formation of glacier algae because there was no glacier bare ice exposed to the radiation. So we started, I'm not showing to look also with correlation with some meteorological data that are collected by a Japanese colleague over this Kanak glacier here, where the access is easier. Zooming out again over Greenland, we are starting to play a little bit with this GCOM-C satellite data. It's from the Japanese space agency, and again we have very fine temporal resolution and very good spectral resolution in the bands that we are interested in, so we can start exploring where algae likes to grow. For example, this area here in north East Greenland, it's really, we estimated the higher concentration ever of glacier algae there. So we are now trying to understand what are the geomorphological or glaciological conditions that favor this formation, or the meteorological forcing on it. In the title I put polar and alpine, so I come back to our closer area here, and if we look again at albedo changing through time, we can see again this simple pattern emerging. So albedo is higher during the winter and then goes down, reaching a minimum in the middle of the ablation season. So we started again to look at this curve here in terms of phenological in a phenological way. So we started speaking about this glacier phenology. So glaciers are somehow breathing as plants, and we can extract some phenological metrics out of this curve here. So for example, the start of the melting season, the end of the melting season, or the minimum reached during or the length of the melting season. So by looking at this modest data in the last 20 years of data, some conclusion came up for albedo. For example, we observed that albedo, the minimum of albedo is getting lower through the years. So that means that glaciers in some part of it, for this is Aletsch Glacier, in some part of the glacier we get decreasing trend of albedo, also in the Alps. And we also observe significant increase in the length of the ablation season by looking at this modest data with glacier phenology. We could not resist to try to link our phenological metrics to surface mass balance. We already mentioned this kind of measurement. We use the WGMS data here, and we try to see if one of these variable is somehow linked with the mass balance. So if one glacier gets very, very low values during the summer, reaches very low minimum, it is also a year with very low, very negative surface mass balance, and the answer is yes, for a minimum of albedo, this one here. So this creates the opportunity to use this model here to try to get the surface mass balance. I'm getting to the end, thanks. By using albedo data that we can reach all over the Earth, also for area very difficult to reach. So my conclusion here is very simple. I mean, it's like we saw different kind of satellite data, optical satellite data, like both multispectral or hyperspectral, and what kind of surface properties they allow us to estimate. We talk about darkening processes, and we learn that there are different things that are going on over the surface of a glacier, where we can have both organic and inorganic impurities, and they compete in depressing the albedo during the summer. Actually, I was okay. Sorry, and the satellite data needs in situ validation, because we need to go in the field and say if this concentration are reliable, and we have to develop new protocols to validate those data, because it's you know, if you ever been on snow and ice, there is a lot of variability, and one point measurement cannot be very reliable. That's it. I would like just to acknowledge 2 new projects that CNR granted me, so for continuing this kind of research on darkening and albedo analysis over the Arctic. Thank you.
Thank you very much, Biagio, for the talk. Now we move to the last one, which will be given by Chiara Crippa. She's a senior researcher at the Institute for Earth Observation of Eurac Research, and the talk would be about assessing Alpine permafrost degradation impact on infrastructure and geohazard.
Okay. So first of all, thanks everybody for being here before the lunch break. And I will try to be short. This presentation is in collaboration with Antonio Bratus, who is also here in the room, and for technical questions, so address him, please. So we talked about glacier snow and remote sensing, and now we are diving into a topic, permafrost, that is actually invisible from the space, from remote sensing analysis. But first of all, to be on the same page, what is permafrost? Because permafrost is not doesn't refer to a specific lithology or ground type, but it's just a thermal definition. So with permafrost, we refer to any kind of lithological medium that can be rock fracture, dry, saturated rock, soil, that stays at negative temperature for at least 2 consecutive years. So, for example, we can have a rock mass that is affected by permafrost conditions. And as we know, rock mass is much heterogeneous. So we can have dry and saturated rock portions inside the rock mass, but also fractured portions filled with ice, or also empty, and then also ice lenses. Whatever the composition of the rock mass, if we have a warming of the permafrost, what we experience is a reduction in the shear strength. So all the rock mass experience a weakening. And this is proved by some lab experiments where we see, for example, that an increase in temperature in samples saturated, so rock samples saturated, we have a decrease in the shear strength going from very low temperature, so -8, -5 degrees, towards less negative temperatures. Same if we consider a fracture, in this case filled with ice, we can explain the failure mechanism according to a Moore-Coulomb law that links the failure mechanisms to the shear strength. And the shear strength is controlled by two parameters that are friction and cohesion. These 2 parameters depend on temperature. So if we increase the temperature in the rock mass, and in this case in the fracture with the ice filling, what we see is that there is a decrease in the apparent friction angle and also a decrease in the cohesion. So we experience a weakening of the strength of the fracture. Same if we just consider ice, we have a weakening of the ice properties going from very negative temperatures toward less negative ones. So this means that even if we don't reach the thawing of the permafrost, just a simple increase in temperature, still being in the negative domain, brings the rock mass to be weakened. And same for the soil. So if we go now to analyze a soil transect, in the static equilibrium, we have, for example, a permafrost body with an uppermost active layer. And the active layer is the portion of soil that experiences the seasonal thawing and freezing. So we start from this condition where the active layer is, of course, in contact with the atmosphere, and all the energy exchanges are driven by this portion. We go then in summer, we have thawing, and the active layer deepens. So the initial permafrost table deepens, and what we have in the active layer is that the ice becomes water, and so water flows and increases the pore pressure inside the active layer. As consequence, we have a rearrangement of the particles inside the active layer and also a reduction of the shear strength, as I showed you before for the rock mass case. Then, if we move to winter conditions, we have a refreezing of this active layer. And so there is a frost heave that induces an uplift of the soil. Water becomes ice back, and so we have an increase in the cohesion, in the properties, in the mechanical properties of the soil, as also shown here by the peak resistance, the peak shear resistance of the rock that increases. But if the freezing is not total, we can have some thallic formation. And the thallic is like a layer of unfrozen soil that weakens, of course, the stability of this portion of ground. So these are the main schematic mechanisms that affect permafrost degradation and permafrost thawing and freezing. But if we look then from the outside, what we see is this. So we have a lot of huge instabilities, small ones and big ones, that are controlled by permafrost degradation. And these are, for example, rock walls, rock avalanches that then developed in other events, so cascading events. For example, the Pitz-Cengolo one that started as a rockfall and then evolved also as a debris flow invading the valley, or the Pitz-Scherchen one, the most recent one. They are all due to an increase in the temperature rock mass that not mandatorily reached the thawing condition, but also experienced a simple transition from negative temperature to less negative ones. And so natural hazards that can affect infrastructures. And in fact, if we look on live pages or newspapers, we see more and more titles showing that also infrastructures are affected by this deformation of permafrost directly. So if the hut, for example, or the road or what else is built on permafrost, but also indirectly if the structure is hit by a rockfall or debris flow. So now let's move to the infrastructure side and let's look a bit into detail of what are the potential destabilization processes affecting the infrastructure. So there are many, and we can group them into groups, let's say. So an infrastructure built on permafrost can experience degradation of permafrost with associated landslides, thermokarst, and destabilization of the ground. But also the pillars, the foundation of the infrastructures can experience these deformations. So with cracks in the walls, dislocation of walls or pillars, and so on. And we don't have to just think that permafrost affects the infrastructure, but it's a loop, because the infrastructure itself affects the permafrost condition because of the changed condition over the ground. So we have an increased load of the infrastructure over the permafrost site, but also, and this is very important, there is also a thermal bridge of the infrastructure with the ground. So the temperature is driven to the ground in a different way where we have an infrastructure and where the permafrost is in pristine condition. So when we plan the infrastructure construction, we really need to take care of the material we use, because there is a high risk of inducing strong changes in the permafrost conditions. We can then classify the infrastructures in different groups according to their sensitivity and consequences related to permafrost degradation on them. And the question that bumped in my mind is always, is the game worth the candle? So if we have these destabilization processes in the infrastructure, should we fix them? How can we cope with them? Should we relocate the infrastructure, fix it, or just abandon it? And this is a question that I can't answer because it's not my topic, and the managers of the infrastructures should answer to this question. And especially the managers on the infrastructures have two different strategies that they can employ to deal with this complex evolution. One is the reactive resilience, and the other one is the proactive resilience. So in the first case, the reactive resilience involves modification to the infrastructures. So we have a wall that is dislocated, that is collapsing. We build some measurements to fix it. For example, now there are some pillars of the cable cars that are built on rails so that they can accommodate the dislocation of the ground. And the other strategy is the proactive resilience. So instead of fixing the infrastructure, we work in advance and we implement a system of measurements and solutions that can control, that can not prevent, but help us to understand which can be the evolution of the permafrost condition. And we are now working in this direction together with Antonio in a project that we are carrying on right now. The project is called the Frostini. It's an Interreg one, and in this project we really focus on the application of remote sensing techniques and in situ characterization to understand which is the most suitable measurement technique to check, to monitor the effects of permafrost stabilization on the ground. I mainly work with remote sensing techniques, and this is why I'm not talking about that today. Because when we talk about infrastructures, in situ characterization is much more effective than remote sensing ones, unfortunately. I mean, the inside analysis and remote sensing techniques, of course, are powerful, but sometimes we really have to check what we can't see from the space, from the ground itself. And so let's adopt some thermal measurements, resistivity, and seismic analysis. Just two examples. These are some analyses we carried on in Gravand Ridge in Valsenales. This ridge has a viewpoint, a very touristic one at the top, and here there is the cable car station. The ridge is now cross-cut by two boreholes, and one of the two is instrumented with thermometer chains for a total length of more than 100 meters. And what we measure is the temperature change inside the borehole. This is important because we want to see if the active layer, so the outermost portion of the rock, is changing, is thickening or shrinking. And this can help us to relate these temperature changes with an increase or a reduction, potentially, of the rock falls on the sides of the crest. And also, we have a baseline temperature for the permafrost condition in the middle of the ridge. It's around -2 degrees all over the seasons. Another way to model, to study permafrost, especially if we want to see the spatial extent, is adopting geophysical measurements. In this case, we carried on some geophysical analysis in Tofane site around the chairlift station. And so a high resistivity means presence of permafrost. What we see under the chairlift station is that there are no permafrost condition because the resistivity is very low, while we have permafrost on the side of the infrastructure. And so is this real? To check this, we adopted also seismic information, seismic analysis, and what we see is that, on the contrary, the seismic analysis showed a presence of ice under the station. So why? Because under the station there are some metallic piles that induce this anomaly, and so it is very important while working with this topic, infrastructure and permafrost, to really select the most suitable acquisition technique. So just the take-home messages. Permafrost degradation impacts the infrastructure stability, but also infrastructure affects the permafrost status. There are two different kinds of strategies we can adopt, and we are now working on the proactive strategies instead of the reactive ones. And while doing this, we always have to take into consideration the monitoring techniques we are using, because the infrastructure is really something difficult to study when working with this frozen material that is permafrost. And with this, I thank you all for the attention.
Thank you very very much, Chiara. So I think we are at the end of the session. I don't know if there is any one quick question or comments to the colleagues. Yes.
Bartek Lux, Institute of Geophysics, PAS. I get comment to Biagio. Within Liquid Ice project, our partners from Geos, they just developed albedo product, reaching to 1984. It's like based on AVHR. Now it's 5 kilometers, but it's like nearly daily as Jason Box and Rasmus Bachbach, they were working on optimization of those data sets. Would it be like of interest for you?
Yeah, for sure. So we can try to see what happened in the past. Fusing AVHRR and MODIS, we can try to see where the trends are receding. If there is some period with the decreasing albedo in some part of Greenland and some other are getting brighter for some reason.
Yeah, well, in the future, there's a plan to have like in high resolution, like 500 meters, probably like in 2 years. And one comment to Francesca. Well, since more question, like since you told us about, like what comes in, that's the major problem. Do you do any data assimilation, like remote sensing or in situ data? Absolutely. Okay. Yeah.
This is all those simulations, thank you. All the simulations I was showing are informed by a very large amount of both remote sensing and ground. So we do plenty of field work in all those regions, but we also use plenty of remote sensing from albedo, from ice velocities. Absolutely. But this was my point, that if you use empirical models, you can't do that. Or you will have a lot of equifinality, right? You need physically based models to be able to assimilate data.
That's true. Yeah, thanks.
Other question or comments to the speakers? Okay, if not, I thank you the speakers a lot for their talk and also all the presenters. And I think that we can also profit of the lunch break to further discuss the topic. Thank you again.